All right, everyone, I'm back for part 2, and we're going to start talking about the elimination reactions E1 and E2. Okay, so let's go ahead and give ourselves a title. So elimination. And these reactions are going to be the E1 and the E2 reactions. Okay, so the E standing for elimination, and then what do you think the 1 and the 2 stand for? Well, the 1 stands for unimolecular in terms of rate, and the 2 stands for bimolecular in terms of rate. All right, so before we jump into the E1 reaction, which is the first one we'll do, I want to go ahead and just remind you what we're going to see in our elimination reactions. Okay, so we're going to see that we essentially eliminate HX from the molecule to form a pi bond. Okay, so we're going to eliminate HX to form an alkene. Okay, so in the elimination reactions, both elimination reactions E1 and E2, we're going to take an alkyl halide and we're going to convert it into an alkene. Okay, and so a few things we're going to have to talk about here. One will be different mechanisms that we can operate under to afford elimination. Some other things we'll have to consider is, if there's more than one alkene product that can form, how are we going to determine which alkene would form? And we'll also have an issue with the E and Z selectivity of the reaction. Okay, and those various issues, where the alkene forms and the EZ geometry of the alkene will depend on what mechanism we're considering E1 and E2, among other factors. Okay, so we're first going to start with the E1 reaction. Okay, so a reminder what the 1 stands for. It means that it's unimolecular in terms of the rate. So let's look at an example E1, a typical E1 reaction. All right, so you might be looking at this like, that's funny. About 20 minutes ago, you used this as an example for an SN1 reaction. What's the deal with that? Well, it turns out that SN1 and E1 are very closely related in terms of their mechanism, and they often actually occur together simultaneously, and we'll see why that is in the mechanism. Okay, but here we have a tertiary halide, weak nucleophile, a polar protic solvent, and so we would get the elimination product, E1, and the SN1 product. Okay, so we end up getting both E1 and SN1 products under these reaction conditions. So it wasn't just as simple as SN1 versus SN2. Now we're seeing that E1 and SN1 are also occurring simultaneously. Okay, so let's look at the mechanism, which will help us understand why we can arrive at both an elimination and a substitution product under the same given the same reagents. Okay, so the mechanism. So the mechanism starts off in the same way that the SN1 mechanism starts off with. So we have our slow, rate-determining step, which was formation of our carbocation. All right, so we know one fate of our carbocation, which is our nucleophile, in this case methanol, attacks the carbocation to give us the SN1 product ether shown. But what else could happen to that carbocation? What if methanol, instead of acting as a nucleophile, acted as a base? Okay, where would an acidic proton be in this molecule? Okay, so if I look one carbon over from the carbocation, what if methanol removed one of those hydrogens? And what if we then donated those electrons in the, to form the conjugate base into the carbon-carbon bond to make a pi bond? So that's going to give us the E1 product. Okay, so you could have also, at the same time drawn the SN1 mechanism. Okay, so the rate determining step of both SN1 and E1 is the same, and that's formation of the carbocation. And then since methanol and other SN1 suitable nucleophiles are not particularly strong nucleophiles or particularly strong bases, they operate as both a nucleophile and as a base. And that's why we get both the SN1 and the E1 products occurring simultaneously or forming simultaneously. So here we showed the mechanism to get to the E1 product. And at the same time, some fraction of the molecules are going to undergo an SN1 so that we're going to get product mixtures, two different product mixtures. So the E1 and the SN1 products forming at the same time. Okay, and we'll write that formally out when we're done talking about E1. Okay, and so let's think about what the rate expression for this would be. So the rate expression would be our rate constant K times the concentration of our electrophile. Okay, so unimolecular. And what do you think the rate would depend on? So the rate is going to depend on the stability of the carbocation. So the rate depends on carbocation stability, just like the SN1 reaction. So as we increase the rate of the SN1, we also increase the rate of the E1 reaction. Okay, so let's talk about then the regioselectivity. So what would regioselectivity mean for an elimination reaction? So here it would mean where the alkene is forming. Okay, so let's look at a starting material, an alkyl halide, that could give us two different products. Okay, so here's our alkyl halide. We'll look at this tertiary bromide and we'll react it under SN1E1 conditions. Okay, so we have two possible E1 elimination products we could form. Okay, and so how do we get to that? Well, let's look. So we could form our carbocation, and then we have two different sets of hydrogens. So I have these secondary hydrogens that I could remove, or I have these primary hydrogens, which would be the same. So this carbon and this carbon, those are equivalent. So we would get the same product if I remove the hydrogens from either one of those carbons. Okay, so how do I decide which protons to remove in the E1 reaction? Okay, well, let's draw the possible products out and compare them. Okay, so if I were to use our water to remove one of these blue, oops, of course that I'm erasing. All right, so let's try to remove one of those blue protons. So we'll call this pathway A, or if we were to remove one of the red protons, we can call that pathway B. All right, so we would have A and we have B. So one product would be this, and then the product through pathway B would be that. Okay, so what's different about those alkenes? Do they have the same stability or different stability? All right, well, they have different stability, right? Because they have a different substitution. So through pathway A, I have formed a tri-substituted alkene, and through pathway B, I've generated a di-substituted alkene. Okay, and so just like we had, a regioselectivity for electrophilic addition to alkenes, like Markovnikov, anti-Markovnikov, we have a regioselectivity rule to follow here too. It's called Zaitsev's rule. All right, so let me write that out and then we'll see how it applies. Okay, so the regioselectivity rule, so this is a regioselective reaction, and the rule we're going to follow is Zaitsev's rule. So Zaitsev's rule says the major product is the more stable product. And we know that for alkenes, that's going to be the more substituted alkene. Okay, so what would be the major E1 product for our above reaction? So it would be the one on the left, right? Through pathway A. So this is Zaitsev's product, and it's the major E1 product. Okay, we still have to consider the SN1, so this is the major E1 product. Okay, so this other molecule over here through pathway B would be the minor product, okay, minor E1 product. And we actually have a name for the minor elimination product. It's called the Hofmann product. Okay, so Hofmann is going to be the less substituted alkene, and it's the minor E1 product in this reaction. Okay, so let's go back up to, where we first drew this example, and let's go ahead and draw what the predicting of the major products would be. Okay, so we would have our major E1 product plus our major SN1 product. Okay, so we have E1 and SN1 forming simultaneously. Okay, so that would be the products that you would want to draw if you were predicting the products of this reaction. Okay, so the last thing I want to mention or write out about the SN1 or about the E1 is just, in terms of its competition with SN1. All right, and as you maybe have realized as we've been working through the last couple of examples is that we're going to write both the SN1 and E1 products from the same reaction conditions. There might be times where you have a slight excess of SN1 over E1 or vice versa, but using paper chemistry, we're not going to worry about that. We're always going to put the SN1 product and E1 product together. Okay, so let's make that final note about SN1 and E1. Okay, so SN1 versus E1. Okay, so the same reaction conditions favor both the SN1 and E1 reactions. Okay, so both reactions occur in the same reaction mixture to afford a mixture of products. Okay, so therefore, both reactions occur in the same reaction mixture to afford a mixture of products. Okay, and again, that would be SN1 plus E1. Okay, so whenever we could use our criteria we talked about earlier in class today of deciding between, SN1 and SN2. If we predict that an SN1 reaction is going to dominate, we are also now going to include the E1 product to go along with that. Okay, so I want to go ahead and look at just one more example of that, of SN1 and E1 products. Right, so here's an example reaction. Okay, so we have our tertiary halide with our weak nucleophile, weak base, polar protic solvent methanol. And so we would get a mixture of E1 and SN1. So the E1 product would be our more substituted alkene, and then our SN1 product would be our ether product. Okay, so that one we didn't have stereochem necessarily to consider, so let's look at one last example of SN1 and E1 together. Let's try to think about something we haven't talked about recently. Okay, so here we're going to consider the reaction of, I'm going to get rid of one of those. Sorry to change that as I was thinking about that answer. Okay, so let's look at this secondary halide and its reaction with water. So it's a secondary halide with a weak nucleophile, weak base, polar protic solvent, SN1. And we also know now that it will give us the E1 product along with it. Okay, and I chose this example because I wanted to make sure we could all remember how to draw a carbocation rearrangement, which was a ring expansion. So I chose this example for that reason. Okay, so we'll end up with this secondary carbocation, and then when we do the ring expansion, that's the mechanism. Remember, we have a carbocation directly outside of a strain 3, 4, 5-membered ring. We'll go ahead and do the ring expansion. So in this case, we would get to that carbocation, and this carbocation then is going to lead us to both the SN1 and E1 products. So if we wanted to draw the E1 product, again, we want Zaitsev's product, so we would form this tetra-substituted alkene, and the SN1 product then would be the substitution product from that carbocation. And we have some stereochem to consider here. So regardless of what the chirality of our starting material was at this chiral center, we've gotten rid of that stereochem when we go to the carbocation. And so here we've generated 2 chiral centers here and here. So you would have all 4 stereoisomers. And you could draw all 4 of those out. Okay, and that takes care of the SN1 products. Okay, so in this case, we saw that the secondary halide was going to undergo this SN1-E1 reaction, or SN1 and E1 reactions together, and the SN, following the carbocation rearrangement, we got this 6-membered ring. We formed the tetra-substituted, more stable Zaitsev alkene for E1, and then for SN1, we rationalized the formation of 4 stereoisomers in that we generated the 2 chiral centers. Okay, so I think we're going to go ahead and stop part 2 here today right now, because what I'm about to start talking about is the E2 reaction. And the E2 reaction ends up taking quite a while, so we'll probably spend most of Monday's lecture talking about the elimination E2, because there will be some other regioselectivity issues for the E2 reaction. We'll actually see that by changing the base, we can affect the regiochemistry, Zaitsev versus Hoffman. We're also going to talk about the stereochemistry and the stereospecificity of the E2 reaction. So we'll see that depending on the chirality of the starting material, we could afford an E or a Z alkene. And one thing I should mention is I just said that for the E2 reaction. For the E1 reaction, since we go through that carbocation intermediate and we have free rotation around the carbon-carbon bonds, at the stage of the carbocation, will generally form the more stable alkene in terms of both substitution and easy geometry. Okay, so I hope you guys all have a nice weekend. I'll be back on Monday to talk about the E2 reaction, and then we'll finally be able to play the world's most fun game, which is SN1 versus SN2 versus E1 versus E2. All right, see y'all then.